So we've been talking about buffers, and now we're going to talk about titration. So this is a brief review of titrations. In an acid-base titration, we have a solution with a known concentration, and we react that with a solution whose concentration we do not know. One of those solutions is an acid, the other is a base. By measuring the volumes and using a little stoichiometry, we can calculate the concentration of the unknown solution. How do we measure out a stoichiometric amount when we don't know the concentration? We monitor the pH as we're adding the known solution, and we can do that either with an indicator or with a pH meter. Now, an indicator is what you've done in Chem 1A. At the equivalence point, the number of moles of acid is equal to the number of moles of base, and the titration is complete, and the indicator changes color. So, should be familiar pictures. Here we've got base in the burette and acid in the flask, and we're using a phenolphthalein indicator. As we add base to the acid, it begins to neutralize the acid and the pH starts to go up. We add more, and now we're seeing a little localized color, but when we swirl it, the color goes away, and this is when we've gone way past the endpoint for illustration purposes only. So we can graph the pH of a solution versus the volume of titrant, known solution that's added. This is called a titration curve or a pH curve. So this titration, or this pH curve here, represents titrating 50 milliliters of 0.1 molar hydrochloric acid with 0.1 molar sodium hydroxide. And we see this very typical curve here, and there's an inflection point in the middle, and that is the equivalence point. Near the equivalence point, the pH changes very rapidly. So we start out over here, we add some sodium hydroxide, and we begin to neutralize the acid. The pH creeps up. When we get to near the equivalence point, a little bit is going to have a big difference, and half a drop can send you way past even. The shape of the curve depends on a lot of factors, including how strong the acid is and how strong the base is. Any questions yet? Yes?
So at the equivalence point, because it goes up so hard, does that mean we over-titrated? So if we titrated it better or like just right, it wouldn't go up as high. At the equivalence point, it would go plateau again?
Well, if you keep adding, it's going to do this. And what we do when we're using a pH meter is we intentionally go past. And we take data points all along, and then we actually graph it out. And then we can calculate where the inflection point is. When you're doing it with an indicator, you're limited by where the indicator changes color. But the difference from down here to up here is probably only one drop.
Right.
So we can't be too far off if we're adding one drop and the color changes. Any other questions? Yes?
Within that one right there, I forget what you said it was.
The inflection point?
The inflection point, would that be equilibrium as well?
Well, the solution reaches equilibrium after every addition.
Okay.
The reaction does whatever it's going to do, and it hits equilibrium before we add any more. Yeah. But this is where, here the slope of the line is positive, and at this point the slope switches to negative.
For the moles of the
No,
base
that's
and
not
the
right.
acid.
There's something else. It's the rate of change.
For the moles of the acid and the base, that's what I was saying.
Yes, here the moles of acid would equal the moles of base.
Okay, that's what I meant.
Yeah. I'm rusty on my math junk. So we're going to consider first the titration of a strong acid with a strong base, so like HCl with sodium hydroxide. We're going to consider 25 milliliters of 0.1 molar HCl being titrated with 0.1 molar sodium hydroxide. here's the balanced chemical equation for that reaction, and we're trying to calculate the volume of sodium hydroxide required to reach the equivalence point. Now, if you're really on top of things with titrations, you could look at this and say, well, it's 25 milliliters. But let's see why. So this is Avogadro. He's a mole, right? We're real familiar with moles. This is millimole. She's smaller, okay? We're going to become good friends with millimole, and I hope to show you today how millimole makes all these kinds of calculations much, much simpler. Okay, so if we want to find the volume of sodium hydroxide needed to reach the equivalence point, we basically have a solution stoichiometry problem where we have 25 milliliters of this compound HCl, and the concentration is 0.100. The capital M means moles per liter. And the information about the sodium hydroxide is that its concentration is 0.100 moles per liter. And we're trying to find the volume here that is going to react perfectly with this amount of HCl. So it's a variation on the standard stoichiometry. I'm looking for a place to write this. I'm not finding it. I'll put it down here. Grams to moles to grams. All stoichiometry is a variation of that. We always have moles in the middle, like the TV show Malcolm in the middle. There's always moles in the middle. So here, I don't have grams of HCl. What I have is a volume. So I've got milliliters. And I'm going to go from milliliters of HCl to moles of HCl to moles of sodium hydroxide. And then what I'm trying to find here is the volume in milliliters. So instead of ending with grams, I'm going to end with the volume. So I'm going to start out with my 25 milliliters of HCl. And there are 3 arrows in my path here, so I'm going to have 3 conversion factors. And the units here tell me what to put on the top: milliliters, moles, moles, milliliters. So I got milliliters, moles of HCl, moles of sodium hydroxide, milliliters of sodium hydroxide. I know, it's boring.
That's fun.
It's okay. And then we would take the units from here and put them in the denominator. So I get milliliters, and the milliliters cancel out. And down here, I'm going to have moles. And here, I'm going to have moles of NaOH. But the concentration that I have here is moles per liter. It's not moles per milliliter. Now, typically what people do is they convert liters to milliliters and go on their merry way. But I'd like to show you that moles per liter is the same as millimoles per milliliter. So 0.1 moles per liter. If I multiply the top and bottom of a fraction by the same amount, I do not change the fraction. So I'm multiplying the top by milli and the bottom by milli. Any questions? So here, instead of moles per milliliter, I want millimoles per milliliter. And then here, I want millimoles per millimole. And over here, I'm going to have milliliters per millimole. Basically, I have to stop using basically if I'm talking about acids and bases. I just put milli in front of everything, right? So how many millimoles of HCl per milliliter do we have? It's the molarity. And I don't know how I did this to leave just not even close to enough room for anything. Let's see if I can move it over. There we go. Magic. So 0.100 millimoles of HCl per milliliter. The moles in the middle is the mole ratio from the balanced chemical equation. Here it's 1 to 1. 1 mole to 1 mole, or 1 millimole to 1 millimole. I'm going to get rid of this question mark because it's just making things look ugly. 1 millimole to 1 millimole. You might say, well, why do you even write that in there? Because we need the units to work out, right? And I know it's not changing anything, but it's important for the units. And if we get in the habit of leaving that out, then we're going to come across an equation where the mole ratio is not 1 to 1, and we'll forget to include it, and then we'll get the answer wrong. And that's no fun. Over here, millimoles per milliliter. The concentration is 0.1 moles per liter. And again, I'm going to do a little shifting here. So 0.100 millimoles per milliliter. This saves a lot of going back and forth between liters and milliliters. And as we see when we do ice tables, most of the time when we're looking at amounts of moles, they're small numbers, and we get 0.0005, or we have to do it in scientific notation, and it just gets icky. Well, this gets rid of 3 of those zeros at the beginning, and it makes the numbers much nicer. So if we do the math here, what do we end up with? 25 milliliters. It's the same as the volume of the HCl because the concentrations were the same and the mole ratio is 1 to 1. Any questions? So we're going to construct a pH curve for this titration. First, we're going to look at the initial pH before we add any base. So what kind of an acid is HCl? It's a strong acid. So a strong acid, we can think of HCl ionizes completely to H plus and Cl minus. So if I have 0.1 moles per liter of HCl, then I have that's equal to 0.1 moles of H plus per liter. Everybody okay with that? So the pH is the negative log of the hydrogen ion concentration, which is 0.100 molar, and so that is equal to 1.00. And here we have our first point on the graph. Any questions? Now we're going to look at the pH after we add 5 milliliters of sodium hydroxide. So this is where we're going to be using the Ba tables. So before addition, the addition, and after the addition, because we have a solution and we're adding something to it. These Ba tables have to be done with moles, not molarities, because as you add more liquid to it, the volume changes, and that changes all the concentrations. So we're going to look at the moles. So initially here, there were essentially 0 moles of hydroxide ion because it was a pH of 1, right? The concentration of hydronium was 0.00250. I'm sorry, not the concentration. The moles. So what they did there is they took 25 milliliters and converted it to liters and multiplied by the molarity. I changed to something a little more sticky outy. This is the same as 2.50 millimoles. That would be 25 milliliters times 0.100 millimoles per milliliter. Everybody okay with that? So we are adding 5 milliliters of sodium hydroxide. The sodium hydroxide is 0.1 moles per liter. The moles are here. I'm just going to continue doing this in millimoles. So when I add, there's no scribble room here, 5 milliliters of sodium hydroxide, the concentration is 0.1 millimoles per milliliter. How many millimoles have I added? Five times 0.1, 0.5. Aren't those numbers easier to look at? So I have 0.5 millimoles of hydroxide ion, and I have 2.5 millimoles of hydronium ion. They're going to react and form water. So all of the hydroxide ion is going to react. So after this comes back to equilibrium, I'm going to have 0 hydroxide again. This half millimole is going to react with half a millimole of the hydronium ion and become water, but we don't need to worry about the concentration or the moles of water. And so it's removing half a millimole from this value, and so I end up with 0.00200 moles, or 2.00 millimoles of the H3O plus. This is a strong acid and a strong base. The reactions go essentially to completion, and so we don't have to worry about an equilibrium constant or actually do an ice table at all. We do have to look at what's reacting and what's left, though. So we have 2 millimoles of hydronium ion. We need to calculate the molarity, and we have to take into account that the volume has changed. So here's the calculation in liters and moles, and that is the same as 2 millimoles divided by the new volume, which is 25 plus 5 milliliters. Get your calculator out if you don't have it out already. 2 divided by the quantity, 25 plus 5, 0.66666666. 0.667. I'm sorry, 0.0667. Anybody have any questions about that? We reacted, we neutralized some of the acid. And now the pH we'll calculate based on what didn't react. I can't remember what slide is next. No. Okay. So have we answered the question? What's the pH? Actually, no, we have not. We did a whole bunch of other stuff. The pH is the negative log of 0.0667. 1.175, 1.176. So the pH went up a little bit. So that's our second point here. I'm using 3 sig figs behind the decimal because I have 3 sig figs in my molarity here.
Okay.
And it's only the digits after the decimal point in a pH that are significant. Yes?
So with the 6 molar hydrochloric acid that we used, isn't the pH like negative 0.77?
Yes, you can have a negative pH.
Why don't we consider that in these problems?
Well, it's easier not to. It's easier not to do titration with negative pHs just because the graphing and stuff. Also, we don't usually titrate solutions that are that concentrated. We usually will use a more dilute solution, 0.1, 0.5 molar, sometimes 1 molar, but that's pretty concentrated for a titration. One of the things that happens when you mix concentrated acids and bases is that they generate a lot of heat, right? And then other things can get involved, and it can get dangerous. So if you had a strong acid that you needed to titrate, what you do is you would dilute it and titrate the diluted acid, and then you could calculate the original concentration. Any other questions? So now we're going merrily on our way. And here we've got, we're adding 10 milliliters, 15 milliliters, 20 milliliters, and the pH is just creeping up. Would anyone like to see the calculation for any of these? I will do one of them on request.
Yes.
Which one?
Whichever one seems the hardest.
15 seems the hardest because it's not just a multiple of 10. It's in the middle. It's kind of, I don't know. It's not much of a reason. And this is good because we don't have that chart all laid out for us. So we have to figure out, we're adding the sodium hydroxide, how much of it's going to react, how much acid's going to be left. We've got hydroxide ion reacting with hydrogen ion to make water. Now, the nice thing is we don't have to base this on the previous step. We can just start from the beginning again. It's a lot less confusing that way. So before we added anything, how much hydroxide ions did we have? Essentially 0. So we had 25 milliliters of 0.1 molar HCl. There is much less than 10 to the minus 7th moles per liter of hydrogen ions. It's so small it doesn't matter. The hydrogen ions here, we had 25 milliliters of 0.1 molar. How many millimoles is that? 2.5. 25 milliliters times 0.1 moles per liter, or millimoles per milliliter, is 2.5 millimoles. It's the same as the starting point in the last slide because we're looking at the same titration. So we're starting with 2.50 millimoles of that. And then what are we adding? We're doing this middle one, 15. We're adding 15 milliliters of the sodium hydroxide. So 15 milliliters times 0.100 moles per liter, or millimoles per milliliter. What would that give us? 1.5? So we're adding 1.50 millimoles of hydroxide. That's our addition, and then we're going to look at after the addition. So these react in a 1-to-1 stoichiometry. So 1.5 millimoles of this will react with 1.5 millimoles of that. All of this hydroxide will react. And we're back to essentially none. 1.5 millimoles of that reacts with this. It's going to use up 1.5 millimoles. So what we've got left now is 1 millimole of the acid. Are you following me? So we have 1 millimole of hydrogen ion. We're trying to find the pH. We need the molarity. So the hydrogen ion concentration is the millimoles of hydrogen ion divided by the volume. But we've added sodium hydroxide, so the volume has changed. We started with 25 milliliters of the HCl, and we've added 15 milliliters of the sodium hydroxide. So now we have 1 divided by 40, which is 0.025 molar hydrogen ion. I did finish that. There it goes. And so that gives us a pH of 1.602. Any questions? Yes.
This is kind of off topic, but if you had like a really high concentration of both the acid and the base,
Mhm.
could you create like a super saturated solution of sodium chloride?
I don't think you'd make a supersaturated solution. You might make a saturated solution and have some sodium chloride precipitate out.
Okay.
Yeah.
Yeah.
That could happen. Mhm. Any other questions? So the same type of calculation for all three of these points. Yeah.
So 1.5 millimoles of hydroxide reacts with H plus.
Mhm.
Does it matter if the millimoles are lower or higher? And if it's higher concentration of hydroxide, what happens with the excess?
So and we'll see this towards the end of the titration, the millimoles of hydroxide added are larger than the millimoles of hydrogen ion. And so then we'll use up all the hydrogen ion and we'll have hydroxide ion left over.
But that's if the hydroxide is smaller.
This is for when the millimoles of hydroxide added are less than the hydrogen ion.
And then
If it's more, we'll do that later.
oh, okay.
Yeah, it's coming. So we're going by 5 milliliter increments here. And the next one is the equivalence point. We did this calculation at the beginning. It was going to take 25 milliliters of sodium hydroxide to react with the 25 milliliters of HCl. So here we have literally a saltwater solution, right? It's got sodium chloride and water. What's the pH? 7. Why? Because we have added intentionally equal number of moles of hydrogen ions and hydroxide ions.
So we could drink our titrations?
Yes, you probably could drink your
They
titrations.
wouldn't taste good, but
It'd be really, this would be really salty.
wow.
Now, the strong acid, strong base will be neutral. A lot of times, though, we're doing weak acids, and so we'll see that the weak acids end up giving us a basic solution at the equivalence point, and you wouldn't want to drink that.
Well, I mean, if it's pH 9,
Yeah, we'll argue about the alkaline water later. Yeah. It might be a pH of 9, but what concentration? Almost nothing. So here, I mean, we could do the whole calculation, but let's not. We know that the H plus concentration is going to be equal to the hydroxide ion concentration. And at that situation, we have pH is equal to 7. And that's going to happen anytime you're titrating a strong acid and a strong base. Okay, let's go past. This is what you wanted to see, Harleen. We're going to add 30 milliliters of sodium hydroxide. So here's, before we added anything, no hydroxide ion, 0.0025 moles or 2.5 millimoles of the hydronium ion. And we're adding 30 milliliters of 0.1. One of the really convenient things about this is you just take the volume in milliliters, which we almost always use milliliters, you multiply by the molarity, and you've got the millimoles. So 30 times 0.1 is 3. Okay, so we've added 3 millimoles of hydroxide to 2.5 millimoles of hydronium ion. What happens?
You can only react with the hydronium that's there.
Yeah, this hydroxide can only react with the hydronium that's there. So 2.5 millimoles of this will react with the 2.5 millimoles of the hydronium ion. And we'll have 0 hydronium ion. And we'll have half a millimole of hydroxide left. Okay, this is what I'm going to do because I'm confusing myself.
Okay.
There we go.
This is,
Oh, look at that. Magic.
because I want to do it in millimoles.
The proper way.
Well, it's not 0.
It's approximately 0. Okay, so we've got 3 of this and 2.5 of that. So we need 2.5 of each. Those are gonna bang, make water. And what do we have left? We have half a millimole of the hydroxide. Okay? Are we all seeing what's going on there? Because this is important. Okay, so we've got half a millimole of hydroxide ions in this solution, which contains 25 milliliters plus 30 milliliters. So we can calculate the hydroxide ion concentration is the amount of hydroxide ions, and we're using millimoles, divided by the new total volume, 25 plus 30 milliliters. And then we get 0.5 divided by 55. 0.00909 and it repeats. Well, I rounded it to 3 significant figures. It goes 0909.
Yeah, because
Both of those.
you have two past decimal point, is that why?
Well, oh, I see your point. Yes, when we subtract here, we do get down to 2 significant figures. Good catch. So we have hydroxide ion concentration. We can calculate the pOH. The pOH is the negative base 10 log of that number, 2.04. And so the pH equals 14 minus that. $11.96, almost 12.
So it's slowly, so post intervention, it will slowly go to neutral, and once that, if you add that last drop, it jumps to neutral, then it'll just keep jumping more.
Yeah, so you're adding the same millimoles or moles of sodium hydroxide with each addition, but now you've got less and less left to react with.
Right.
And so the percentage of remaining that are left becomes larger and larger, and you get a bigger pH change. And then it'll shoot up to here, and then it's going to be sloped, but almost a plateau. Yes?
Just to like bring math into this, because like I want to connect it.
Mm-hmm.
How would you say that this, like, what's the equation of just shit?
What's the equation of the line?
Like, how does that rate go? Because I'm confused at how it goes so high so fast. If it's just one little increment, so why is that?
Well, this is like taking pure water and adding 5 milliliters of 0.1 molar sodium hydroxide to it. So that would make the pH go up, right? There's nothing to neutralize it. We've used up all our neutralizing power. So now we're just adding more hydroxide ions, and the pH is going to go up.
And does that rate continue?
It does. Well, this is actually technically not a rate, unless you're talking about this change in slope of the line. You've been studying too much calculus, but we're going to see that it's gonna bend over. Kind of makes an S-shaped curve.
Where the velocity is
You're thinking too.
The inflection point. Yes. Okay, I want to show you something that I do with my calculator that makes pOH to pH a little easier. So we've got this 0.009, well, we'll just call it 91. And so I know that this is the pOH. We know that this is the pOH. If I take the log of that, I get a negative number, right? I get negative 2.04. And then if I add 14, I get my answer. Well, I can take the negative log here, and then I'm going to subtract that number from 14. Or I can just leave off the negative, combine the negative from the one equation to the other, and it's just a fast shortcut on your calculator. If you don't like it, don't do it. That's fine. That's fine too. So,
I'm just worried about the sig things.
Like,
oh,
Yeah.
the previous one, like the previous poems in this one, there was two significant figures for the molarity, but then the pH.
no, the molarity had three
Oh, no.
significant figures.
Oh, really?
hmm And this one's got two.
Technically, we can just add a 0. Wait.
But we're subtracting. 3.00 minus 2.50 is just 0.50. And so that's the whole adding subtracting thing where you can have more or fewer sig figs than you started with. So I'm glad that you're thinking about this. I really cannot imagine a situation where on a final answer, if you were within one digit of the correct number of digits, how it could possibly be counted wrong in this class. In general, it's always better to write down more, because you can always chop them off at the end. If you realize you need to add them back, you have to go back and do the calculation of it. So these calculations will be very similar, adding 35, 40, 50 milliliters of sodium hydroxide. And the pH is going to go up. Now, the reason that the pH does not change greatly here is because pH is a logarithmic scale, and we are adding on a linear scale. Okay? So going from here to here, we change the concentration of hydronium ions from 10 to the minus 7 at neutral to 9 to the minus 2, something like that. That was like a, 10,000 times increase. And so then we see a big jump in the pH. Here, when we're going from 0.09 up to a little bit more, that change is very small in terms of factors of 10 on a logarithmic scale. And so that's part of the reason for the weird shape. It's a log scale. So here's the overall curve. So the initial pH, and before the equivalence point, we have hydronium ion in excess. Here we have the equivalence point when it's strong acid and strong base. This will have a pH of 7. And then after the equivalence point, we have excess hydroxide. Any questions?
Technically, even right before that equivalence point, it's still in excess, right?
Yes, it's in excess right up until you get there. Yeah.
If we did a different type of titration where instead of titrating an acid with a base, you did a base with an acid, would the titration go the opposite direction?
I'm so glad you asked. Yes, you can titrate a strong base with a strong acid, and the curve is very similar, but it starts basic and goes acidic. We still have the equivalence point in the middle at a pH of 7. Here, this part has an excess of hydroxide, and now we have an excess of hydronium ion down here.
And the calculations would still
The calculations would be the same pattern. You just have to pay attention to your hydroxides and your hydrogen ions. Isn't this fun? Okay, so we don't usually go around calculating an entire pH curve. That was to learn how to do it. So here's just, we're going to calculate one point. A 50 milliliter sample of 0.2 molar sodium hydroxide is titrated with 0.2 molar nitric acid. Calculate the pH after the addition of 60 milliliters of the nitric acid. So strong base and strong acid. So we can look at this as we're adding H plus to the hydroxide, and that's going to make water. So how many milliliters of hydroxide do we have to start with? We have 50 milliliters. I meant to say millimoles. Tried to save it there. 0.2 moles per liter, which is 0.2 millimoles per milliliter. So I think that's 10. Right? Because 2 times 50 would be 100, and then you move the decimals, so it's 10. So we're starting out with 10 millimoles of hydroxide. That's our before. Our addition is 60 milliliters of 0.2 molar nitric acid. So 60 milliliters times 0.2 molar. I believe that's going to be 12 millimoles. So we're adding 12 millimoles of acid. We started out with essentially 0 hydrogen ions, and we're not adding any. So after the addition, after this reaction occurs, what's going to be left over? 2 millimoles of hydrogen ions. These 10 millimoles of hydroxide ions will be neutralized by 10 of the millimoles of hydrogen ions. And so then we're going to have essentially 0 at the end. So that's hydrogen ion. So the hydrogen ion concentration is the moles divided by the liters, or the millimoles divided by the milliliters. 50 plus 60 . So that's 2 divided by 110. And that would have 3 sig figs. pH. I have that number in my calculator. I just take the log and go up and grab that number. And I'm going to get 3 sig figs 1.740. It's not a very good 7. It's not a negative number because the pH is the negative log. Yeah. Any questions? Yes. Say that again. Yeah, for the others, we were starting with acid and adding hydroxide, and so this was 0. The hydroxide was 0. It's 0.00000001, right? And so compared to this, it's nothing. Any questions? This works for strong acids and strong bases. As you can imagine, things get a little more interesting with weak acids and weak bases. Any last questions about this one? There's the answer. Okay, titration of a weak acid with a strong base. And this is a very typical thing. Like if you're titrating KHP, potassium hydrogen phthalate. Yes, there's a missing slide. Okay, so before we go to the weak acid, we're going to look at this conceptual connection. So this is looking at pictures. So the amount of strong acid in the flask shown here is going to be titrated by the strong base in the burette. Which mark on the burette, A, B, C, or D, indicates the amount of base required to reach the equivalence point? I'm hearing D, and that is correct. So we have 1, 2, 3, 4, 5, 6, 7 hydrogen ions in the flask. So we're going to need 1, 2, 3, 4, 5, 6, 7 hydroxide ions to neutralize them. Does that make sense? Sometimes with the smaller numbers and the pieces you can see, it makes more sense. So there's D. And now to this slide. So we're going to look at titrating formic acid, HCHO2, with sodium hydroxide. So the first thing we're going to do is calculate the volume of sodium hydroxide required to reach the equivalence point. And as it says at the bottom, the volume at the equivalence point only depends on the amount of acid, the moles of acid, not on the strength. So we've got 25 milliliters of the formic acid, and it's 0.100 millimoles per milliliter. And it's a 1-to-1 stoichiometry, 1 millimole of sodium hydroxide to 1 millimole HCHO2. And the concentration of the sodium hydroxide is 0.100 millimoles per milliliter. And ta-da, we get 25 milliliters. Yes?
I'm curious why the volume doesn't matter when, if Ka gives the amount of hydrogen ions that are actually dissociating, or hydrogen ions that are dissociating and turning into hydrogen ions.
Well, the thing about the weak acid is there's this equilibrium, and as you add base to neutralize the ionized hydrogens,
More
it shifts,
Okay.
and it'll just keep shifting until it's all used up. Yeah, that's an excellent question. And it's nice because we can do titrations in Chem 1A and we don't have to talk about this.
Well, I
Save
asked
it
you
for-
about it. Because the other students didn't care. So
Yeah. Okay, so starting at the beginning without adding any base, calculate the initial pH. So this is the type of ice table calculation we've done before. So here we have the initial concentration of the acid, and it's going to ionize, it's going to form hydronium ion and formate ion. The change is going to be minus X, plus X, and plus X. And so this is 0.1 minus X, X, and X. And here I've given us the Ka for that. So the Ka, 1.8 times 10 to the minus 4, is going to equal X squared divided by 0.100 minus X. Most of the time, the X's small approximation works. And I think this is actually written out on the next slide. No, it's not. I remembered something else. So if X is small, we can disregard the X down there. And X is equal to the hydrogen ion concentration at equilibrium, which is going to be 0.00424. Anybody else get that? pH is 2.37.
I got 415.
You got 415
Yeah.
It's in any solvent.
with the solver? Okay.
It just puts the pH off by 0.01.
Yeah, so if we check the X's small approximation, we get 4.24% or 4.2%. So this is getting close to not being able to use X's small. So it was 2 point what?
415.
No, the pH.
Oh, pH is 2.38.
2.38. Okay, so that gives us a difference of 1 in our uncertain digit. Yeah,
So either way.
either one would
As
be
long as the
correct.
percentage.
Any questions? We're going to add 0.5 milliliter of sodium hydroxide. So when we add the 0.5 milliliter of sodium hydroxide, that is going to convert a stoichiometric amount of the acid into its conjugate base. And now we have a buffer solution. So I am going to get rid of these moles again. I actually thought about redoing the slides, but it sounded very tedious at 4 in the morning. So adding 5 milliliters of 0.1 molar sodium hydroxide. So that is 0.500 millimoles of sodium hydroxide. We initially had 2.5 millimoles of the acid. So we have 2.5 millimoles of acid. We add 0.5 mole of base. That's going to neutralize 0.5 mole of the acid. So we're going to have 2 millimoles of acid left. Now we have to think about what's on the other side as well. It's going to make half of millimole of the conjugate base. Yeah, ask. Mm-hmm. So when the hydroxide reacts with the acid, for every one of these that reacts with one of those, we're going to make one water molecule and have one of these anions left. So if I react 0.5 millimoles of hydroxide ion, I'm going to end up with 0.5 millimoles of the conjugate base. Yeah. We didn't do this with the strong acid, strong base, because this was chloride ion, which is pH neutral. But now it's a weak acid, and so it's not pH neutral anymore.
So the addition of the hydroxide will equal the after addition if it's a weak acid.
Yeah, so we're still looking at a stoichiometric addition and reaction. Now, are these going to be equilibrium concentrations? No. But it's going to go, it's best to think of it going there, and then it's going to come back a little bit. And we'll use the Ka to tell us what it's going to be at equilibrium. Nope, it's not there either. I'm imagining things. So what we need now are concentrations for an ice table. Oh, no, I know. We need concentrations, but we don't have to do an ice table because this is a buffer. We can use the Henderson-Hasselbalch equation. Hassel what? Hasselbalch. Yeah, be thankful for your own name. So the concentration, it always reminds me of David Hasselbeck. We've got 2 millimoles of weak acid left, but our volume has changed. We have 25 milliliters plus 5 milliliters. Right? So 2 divided by 30, 0.0667. And our conjugate base concentration is going to be 0.500 millimoles, also divided by that new total volume. Bless you. 0.0167. So the pH equals the pKa plus the log of the base over the acid. There's our Ka. Our pKa is 1.8 times 10 to the minus 4, and the negative log of that, 3.74. Yes. Yeah, to get the pKa, I took the negative log of the Ka. And sometimes in tables you'll look it up and it'll actually show you both, and so you can just pick it out, which is nice. So the pH is equal to the pKa plus the log of the conjugate base concentration divided by the weak acid concentration. Did I do it wrong? When I did it with rounded numbers, I got 4.33. What are you getting? Yeah, because this is not right. I upside down them. I typed them in my calculator wrong. I had the concentration of the acid and the base reversed. I wrote it correctly and I put it in my calculator wrong. There we go. .14. Now we're happy, right? And that looks like it matches that point a little better because it's clearly less than 4. Any questions? We can use the Henderson-Hasselbalch equation because it is a weak acid and its conjugate base in solution, and so we have a buffer situation. You could make an ice table and do it that way. That always works. You can only use that equation with a buffer.
So if you're given like a random A, and then you try to do the negative log, whatnot, not getting that would be like pH, because it's not a buffer.
Yeah, at the initial you couldn't do that. Like if you tried to use that equation here, it wouldn't work because you actually don't have any of the base yet. And if you tried to use it very close to that, it wouldn't work either. Remember, we had those guidelines. The ratio of acid to base or base to acid needs to be between 0.1 and 10, I think it was. So one can't be more than 10 times concentrated than the other. And we're okay here because 0.016 and 0.066, that's less than 10 times larger. Yeah.
If we were to do an ice table, would those start as our initial concentrations, or we would just do it?
Yes. Yep, these would be the initial concentrations, and then you do the plus x's and minus x, and you plug it into the equation. Yep. Any other questions? So now adding more, moving right along. I want to do this point here because this is what's called the half equivalence point, and it's kind of a special point on the pH curve. So I'm going to do this 12 and a half. So we've got, we're adding hydroxide to our acid. So we're adding hydroxide ion to our weak acid. No, I got that wrong. And we're going to be getting water and the conjugate base. So before we add anything, we have 25 milliliters times 0.1 or 2.50 millimoles of the acid, and none of the hydroxide and none of the conjugate base. And then adding 12.5 milliliters of 0.1 molar sodium hydroxide is 12.5 millimoles. And then after, so no, I didn't multiply by 0.1. This is 1.25. Like, wait a minute. There we go. 1.25, that's better. 1.25 millimoles of this will take out 1.5 millimoles of that, making 1.5 millimoles of this. So this is going to go back to 0. We're making 1.25 millimoles over here. And this is losing 1.25 millimoles. And that ends up being 1.25 millimoles. The sodium's a counterion. It's a spectator. It's just hanging out. So it was hanging out with the hydroxide, and hydroxide got involved with the hydrogen ion from here, and now the sodium's hanging out with this guy if he has to be with somebody. So Henderson-Hasselbalch equation says it's the pKa plus the log of the base concentration divided by the acid concentration. The millimoles of each of these is the same. Are their concentrations going to be the same? They're in the same volume, right? These are equal to each other. So when those are equal, this term goes to 0. That didn't look like a 0. And the pH is equal to the pKa. So the pH equals, what was it, 3.74? That's at the half equivalence point. So that's kind of a special thing. I mean, you can just do a very simple stoichiometry calculation to find out how many milliliters of this base do I need to add to get to the equivalence point. If I divide that in 2, when I've added that much, the pH will be the pKa. Every time. Questions? If you don't remember that it's like this and you had to calculate it, you could just calculate it the long way and it would still work. Let's make sure I didn't forget something. So the pH after adding 25 milliliters of sodium hydroxide, the equivalence point. We have neutralized the weak acid. It's not a buffer anymore. So we have 2.5 millimoles of hydroxide added to 2.5 millimoles of acid. And these are going to completely knock each other out. They're going to completely react and form that same amount of conjugate base over here. The pH here is not going to be 7 though, because this is a conjugate base. It's going to act as a base, and so we now have to look at the equilibrium for the base. So we've got the CHO2 minus plus water is in equilibrium with the weak acid and hydroxide ion. We're starting out initially with none of the weak acid. Well, actually we can say 0. None of the hydroxide. This is the I for initial. 2.5 millimoles. In what volume though? We can't just use the millimoles there. We have to calculate. So the concentration of the anion is 2.5 millimoles divided by 25 plus 25. .05. So we've added sodium hydroxide, we've neutralized all of the weak acid, we've transformed it all into the conjugate base. But because it's a weak acid, the conjugate base is a weak base, and so it will reionize and create some of those hydroxides back. So for the change, this is going to lose X, This is going to gain X. This is going to gain X. Need some space. So the equilibrium expression is x squared over 0.0500 minus x. And what does that equal?
1 over.
That's a step in the right direction, 1 over the Ka. It involves Kw. It's Kw divided by Ka. It's Kb, right? Because this is a base. The reason it's just not 1 over is that this is not simply the reverse of the ionization of the acid, because there's water involved. So this is the Kb, which is 1 times 10 to the minus 14 divided by 1.8. And it's interesting, I did exactly that same thing on the couch with my dog at 4 in the morning and got the wrong answer, and I'm like, wait, what? And then oh yeah, Kw, not 1. So this is a really small number. 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 4. 5.6 times 10 to the minus 11. Is x going to be small? Yeah, this is a tiny equilibrium constant. So x is going to be small, so we can ignore x there. And so I can take my Kb and multiply by the 0.05, and then take the square root of that to get what x is. X is 1.67 times 10 to the minus 6. But what does X represent? Is it the hydrogen ion? No, it's the hydroxide ion. This is the hydroxide ion concentration. We want the pH. So we can calculate the pOH. And subtract that from 14. It was 5.78. The pH is 8.22. The equivalence point for the titration of a weak acid is always basic. Yes?
So reversing the reaction, even when you get Kb, you don't get any 1 over Kb for reversing the reaction.
I'll show you how that works after. Anybody else have any questions? I want to finish this titration because we just can't go over the weekend with this half-done titration. So this is the one where it was all worked out for me that I kept looking for, and yeah, I missed it. There it is. Okay, I already did that. Past the equivalence point. We're adding more hydroxide than there was weak acid. So the hydroxide overwhelms the weak base that gets formed, and the calculation ends up being the same as for a strong acid. We could calculate the contribution from the weak base, but it's going to turn out to be so small that it doesn't matter. So let's just try to look at this with moles instead, because I'm tired of changing that. 30 milliliters of sodium hydroxide, this many moles of hydroxide are same starting moles of acid. So we've got more hydroxide than acid. So we're going to use up 0.0025 moles of the base, leaving 0.0005. And then we're going to make 0.0025 moles of the weak base. The strong base is so much stronger than the weak base that it overpowers it. So we can look at the hydroxide ion concentration as being that 0.00050 moles divided by 0.0250 plus 0.0300. So tedious. Yeah, and then I went and put the wrong number of zeros in my calculator. 0.00909. That's the hydroxide, right? So the POH is going to be 2.04. The pH, 11.96. Which, if you go back and look at the titration curve for the strong acid, strong base, at this point, we've been using the same volumes and concentrations. The pH is the same. Because the contribution of that weak base is insignificant. So then you can go on and repeat that calculation, adding more and more hydroxide, and we get this same result up here. Any questions? Yes?
At some point, does that level off like a straight line, or is it just like for everything?
At some point, would it level off to a straight line? It would certainly appear to be a straight line. Yeah. So here's the overall weak acid with a strong base. So before the equivalence point, we're in the buffer region, we can use the Henderson-Hasselbalch equation. At the equivalence point, we're just looking at a weak conjugate base. We can calculate the pH that way. Afterwards, we've got hydroxide in excess, and the calculation gets much simpler.